Hello, my name is Cameron Forbrigger, and in this video I will be presenting my latest work from the Diller Micro-Robotics Lab at the University of Toronto in Canada. The title of this work is Tailored Magnetic Torsion Springs for Miniature Magnetic Robots. I'd like to invite you to attend my live presentation session, and you can find the details at the bottom of this slide. The motivation for this work is magnetic miniature robots in biomedicine. With magnetic fields, we can apply forces and torques wirelessly to mechanisms with embedded magnetic material. By locating our driving electronics outside of the patient, it saves space on the robot itself for other systems, such as sensing or electric cautery. Low-frequency magnetic fields can safely penetrate both flesh and bone, which makes magnetic actuation an attractive approach for biomedical applications in enclosed spaces, like within the skull, for neurosurgery. The video on the right shows an earlier prototype magnetic tool that we developed in our lab. In this prototype, we used compliant joints of nickel titanium wire to provide a restoring torque that is necessary to achieve multi-degree of freedom control. However, these joints resulted in some unwanted buckling that made it difficult to predict how the robot would interact with the surrounding tissue or when it was manipulating objects. To avoid this buckling behavior, we wanted to investigate designs that use rigid pin joints instead of compliant elastic joints. However, rigid pin joints do not provide the restoring torque that is necessary for multi-degree of freedom magnetic robot control. However, we realized that in magnetic robots, we already have embedded magnetic material for actuation, which you can see here in this example robot. So in each of the moving links, we have some embedded magnetic material that we will use for actuation. But what if we could also use that magnetic material to provide a restoring torque by playing with the interaction between the magnets themselves? Then we could simply add another magnet in the base of the robot, and by changing the relative positions of all three of these magnets, we can control the restoring torque that is present about the two joints. We called this idea simultaneous magnetic actuation and restoring torque, or SMART springs for magnetic robots. In this work, we will show how you can design these SMART springs to demonstrate useful and novel magnetic spring behaviors. Here we will examine the analytical model for the SMART springs and discuss some of the relevant geometry. Here we can show two embedded magnets inside of two links that are connected by a pin joint. We can define a spring deflection between the two magnets as gamma, which is going to differ from the Dinavet-Hartenberg joint angle by some constant angle beta. As the magnets move about the pin joint, or rather as link B rotates about the pin joint, there's going to be interactions between the two magnets that causes some component of restoring torque about that pin joint. This torque is going to be a function of the spring deflection, but also the radial positions of the magnets and their relative orientations. Overall, the spring torque is a function of many different parameters. So to simplify our analysis, we used dimensional analysis to define a unitless torque. The unitless torque tells us about the shape of the torque function rather than its magnitude. And from that dimensional analysis, we were able to greatly simplify the relevant parameters to only three. The dimensionless torque itself is defined by the torque divided by an amplitude constant c, and the R bar value is a characteristic length ratio that describes the geometry of the joint. The amplitude constant is defined here, and it determines the overall height or amplitude or stiffness of our spring. So how do we use this analytical model to come up with a design for our SMART springs? First, we need to consider how we want the robot to behave in response to an externally applied magnetic field. This is the case for any magnetic robot, any magnetically actuated robot. Those actuation considerations will likely determine values for phi A, phi B, and MB. From there, we will consider the spring response shape that we are looking for. This shape could be defined by the location of the equilibrium points, or whether we want, say, a constant stiffness spring within a certain range. Next, we consider how stiff we want the spring to be, or how high the torque should be for a given position. This is determined by the spring response amplitude constant, C. To examine how this works in practice, we will go over two examples. One is a robot with a constant stiffness wrist, or rather, this robot has a constant stiffness wrist, and we will achieve constant stiffness by tuning the parameters of M0 and M1. And then we will also be examining the same robot with a bistable nonlinear response for its finger and an unstable equilibrium point somewhere around 45 degrees that causes it to snap between an open and closed position. And we will achieve that by modifying the positions of M1 and M2, all in the same robot. And mostly we will focus on the spring response shape because that is the unique component of this analysis that is crucial to the design of smarts. First, let's examine the behavior of the wrist joint. Based on the actuation considerations, we decided that the values of phi A and phi B should be 180 degrees and 0 degrees respectively. From there, we can start to examine the behavior of the equilibrium points as we change the characteristic length ratio R, and that is shown in this plot here, where the stable equilibrium points are shown by the blue triangles pointing down, and the unstable equilibrium points are shown by the red triangles pointing up. As you can see, as we change the characteristic length ratio, the number and position of the equilibrium points changes. We wanted to have an equilibrium point at around, or rather a stable equilibrium point at around 180 degrees, and it was easier to manufacture joints that had characteristic length ratios between 0.8 and 1. So we chose that range to really narrow in on. From there, we can look at the specific wrist stiffness in that range of our bar values from 0.8 to 1. And so here we've plotted those responses in several different colors, and we're showing the normalized stiffness as a function of the spring deflection. And we want to have a stiffness that is very nearly constant. And we can see that the one that comes closest to that is at an R value of 0.95. Further tuning would result in an R bar value of 0.94 for this to get the very nearly constant stiffness. We performed a similar analysis for the finger equilibrium points. I won't get into as much detail on this one, but again, we were looking for a certain position for the unstable equilibrium point, and that restricted our range of possible values of R bar to a very small range, which I've highlighted here with this circle. This is a video of our final robot design. After selecting the value of the amplitude constant, we have fully defined our robot, and this is simply to show that the qualitative behavior of the robot is what we were looking for. Although we were hoping for a smoother sort of transition in the wrist, but friction was causing some issues there that made the behavior a little bit jerky. However, we can see that we can control the wrist and the finger independently, and that the finger snaps rapidly between the open and closed stable states. Here we show some quantitative results compared to the qualitative results shown in the video. These results are showing the spring torque in the wrist joint and in the finger joint. And we are comparing the dipole model, which is shown as a black line, to our finite element analysis and our experimental measurements. We can see that there is generally a good agreement between the experimental results and the dipole model. The finite element analysis also agrees reasonably well, although it predicted a very different stable, or rather equilibrium position for the finger than the analytical model predicted. This is likely because of the rather large length to width ratio of the finger magnet, which is not well modeled by the dipole model. However, the experimental results showed very good agreement with the dipole model, so the applicability of the dipole model seems to be quite good for these particular cases. In terms of limitations and future work, first of all, I'd like to mention that due to the limited time, you can find more details on the design, the experimental apparatus, and the finite element analysis in the paper, the manuscript itself. In terms of the limitations of our work, we had non-negligible friction, and we could see that in the video where the robot was controlled and it showed not quite as smooth a behavior as we would have liked. We also had a rather ad hoc design methodology. It would be nice if we could have an algorithm where we could plug in some desired behavior and it would spit out the parameters that we need to achieve a given desired behavior. In future designs, we could have as many as 3 different stable equilibrium points within 180 degrees. And we could also examine cases where the magnets are oriented out of plane, as well as robots that have more than just 2 degrees of freedom. I'd like to thank you all for watching the video. If you have any questions, you can email me at cameron.forbrigger@mail.utoronto.ca. And if you're interested in seeing more from the Diller Microrobotics Lab at the University of Toronto, you can check out our website, microrobotics.mie.utoronto.ca. My colleague, Mohammed Salihizadeh, is also presenting, and you can find his presentation details at the bottom of the slide. Thank you very much.